Hi guys. This week we're getting into gas stoichiometry, including limiting and excess reactant gas stoichiometry. And this is very similar to the stoichiometry we've already done when we're talking about gases at STP, but slightly different when it comes to gases that are not at STP. So we're going to start by refreshing on stoichiometry itself here. So the very key component of stoichiometry is the mole ratio. Everything else are things that we've already done. We know how to convert from grams to moles. We use the molar mass. So right here, grams to moles, molar mass. We know how to go from particles to moles. We use Avogadro's number. We know these conversions here going from volume to moles. We know that at STP, 1 mole is 22.4 liters, so I can use that as 1 mole over 22.4 liters or 22.4 liters over 1 mole, depending on what's appropriate for the conversion. And if it's not at STP, this is where we'd actually have to stop the stoichiometry chain and would solve for either N or for V, depending on what end of the equation you're on. And we're going to go through all of those. So these are things we're familiar with. And the new part when we added in some stoichiometry was the mole ratio. So this here is your stoichiometry map, or the mole map. So what you'll use this for is to help you figure out what conversion factors you need to get from any point A being our known value. So it can be grams of A, it can be moles of A, volume of A, to any point B, which is the value that you're looking for. So whatever it is that we don't know the information about and we're trying to find the information about. So that's our map, and you'll see that repeatedly throughout these slides. And what the mole ratio is a conversion factor that tells us how many moles of something we need given the moles of the thing that we started with that we have. So it's a conversion factor between any two substances in a chemical reaction if it's balanced. That's the key here. You do have to balance these equations. All of the equations in these slides are balanced just to save time, but make sure that you balance any equations that you are working with when you're doing these problems, or it will all be wrong. So for example, if I wanted to know the mole ratio between here, my aluminum oxide and my aluminum. So this here, my mole ratio would be 2 to 4. For every 2 moles of aluminum oxide, I have 4 moles of aluminum being produced. Same thing, aluminum oxide and my oxygen here. For every 2 moles of my aluminum oxide, I have 3 moles of oxygen that can be produced, so on and so forth. So that's going to help us convert from our A, which is our known, to our B, which is our unknown. So for example, a problem that we might have done with this would be if I had 24 grams of aluminum oxide, how many grams of oxygen would be produced? So aluminum oxide is going to be my A in this scenario. So look at my balanced equation. This is my A. And then how many grams of oxygen are produced? Oxygen is my B. So I'm going from grams of A to grams of B. So looking at my chart, the steps that I'm going to end up using here, pick a different color, are going to be from grams of A. I have to go to moles of A using molar mass. And then I have to use my mole ratio to get to moles of B. And then I would use the molar mass of B to get to grams of B. So those are my 3 conversion factors: molar mass of A, mole ratio, and then molar mass of B. So plugging those into the equation, I found the molar mass of aluminum oxide to be 101.96 grams. So I have 24 grams times 1 mole over the mass, and that cancels out my grams. So if you do your cancellation, grams cancel, and aluminum oxide cancels. And now I'm in moles of aluminum oxide. I use my mole ratio for the next step. So I look at my balanced equation and I say, how many moles of oxygen do I have? And that's highlighted in red up here. I have 3 moles of oxygen for every 2 moles, right there, of my aluminum oxide. So that's my mole ratio step, and I can go ahead and continue canceling my units then. So now my moles of aluminum oxide cancel with my moles of aluminum oxide. And I'm in moles of oxygen, but I need to get to grams. The question asked for grams of oxygen. So then I do that last step it says up here, which is using the molar mass of B, which is my oxygen. Oxygen is a diatomic molecule, O2. So I have 16 times 2 gives me 32 grams per mole. My mole of O2 cancels with my mole of O2. I'm left in grams of O2. So now you'd multiply everything on the top across. So 24 times 1 times 3 times 32. Put that all in parentheses in your calculator. And then divide that by 101.96 times 2 times 1. And you'd get 11.3 grams of oxygen. What this tells us is if I start with 24 grams of aluminum oxide and I assume that everything goes perfectly, so I didn't spill any sample, nothing was lost, I should be able to make 11.3 grams of oxygen from this particular reaction. And with sig figs, that is the correct rounded number. So this was our basic stoichiometry problem here. What we're going to do now is we're going to add those volume components into it. So I could start anywhere on this map. I could start at particles and I could go to volume. I could start at grams and I could go to volume. We're going to start by just doing some volume to volume problems just to get used to this. And we'll start with the easier ones, which are the STP problems. Before we jump into the problems, just some background information here for you on gas stoichiometry. So Gay-Lussac is actually responsible, Gay-Lussac and Avogadro, for determining this value here that we use, where 1 mole of gas is 22.4 liters. It occupies 22.4 liters of space. So what happened was Gay-Lussac was studying the ratios between volumes of reactants and products, and he figured out that if I had, say, 2 volumes of hydrogen and 1 volume of oxygen, it would form 2 volumes of water, H2O, which you can see in the little graphic down here. So if I had 2 hydrogen, 1 oxygen, I would get 2 H2O. Gay-Lussac's experiment and figuring Dalton's postulates, which said that we have to have the same number of particles on the reactant side, the same particles on the product side, led Avogadro to the theory that if we have something at the same temperature and pressure, equal volumes of gas have to have equal numbers of moles of those gases. And therefore, instead of reading this as just 2 moles of H2 and 1 mole of O2 produce 2 moles of H2O, we could assume that 2 volumes of H2 and 1 volume of O2 would produce 2 volumes of H2O. So that led to his theory that at STP, 1 mole of any ideal gas always contains 22.4 liters. So it takes up that 22.4 liters of space. And that's how we do our STP calculations. It makes it much easier. So you use that as either 1 mole over 22.4 liters or 22.4 liters over 1 mole, depending on how your units need to cancel out. So as I said, we have 2 types of problems. We have STP and we have not STP. If you don't remember what STP means, it's written right here for you. So STP is standard temperature and pressure, where the temperature is 273 Kelvin, the pressure is 1 atmosphere, and the new thing we're adding in here is that 1 mole of gas takes up that 22.4 liters of space. Very important here. So we have our mole map again, and this we're going to focus on the volume to volume for this next example here. So reading through the problem, these are the steps that you need to go through in order to be able to solve these problems accurately. So step number 1, always balance the equation. Identify what's known and what's unknown. So identify your A and your B. Identify all the conversion factors you need, and you write those right above the chart as well. If the reaction's at STP, it's nice and easy. You're using that conversion factor of 22.4 liters per mole. If it's not, we'll get to that. And then you just set up and solve like a regular dimensional analysis chain from that point forward. So we're going to go ahead and work through this problem. I have it copied again down here so we have a little bit more space. So it says calculate the volume of O2 in liters. So I'm looking for O2, which makes this my B, and it says in liters. So I'm going to put question mark liters there. Reacted at STP. I'm going to make a note for myself that this is at STP. That's required for the complete combustion of 2.64 liters of C2H2. So this is my A. I know the information about this. I know I have 2.62 liters, and I also know that this is at STP. So since both of these are at STP, nice and easy, both ends of them, I'm going to use that ratio 1 mole over 22.4 liters or 22.4 liters over 1 mole. So now that I know my A and B, I can refer back to my chart, and I'm going from, if we highlight here, my volume of A at STP all the way over to my volume of B at STP. So my first conversion factor is going to be 1 mole is equal to 22.4 liters. That gets me to moles of A. Then I'm going to use the mole ratio from that balanced equation. That gets me to moles of B. And then I'm going to use the last 1 mole over 22.4 liters, or reverse actually, 22.4 liters over 1 mole, to get me to the volume of at STP. So starting here, we're going to start by writing down our starting information. I have 2.62 liters of my C2H2. And it said the first conversion factor, I need to use that 22.4 liters per mole. I'm looking to cancel out liters, so liters should be on the bottom in the next step. So 22.4 liters, 1 mole. My next step is the mole ratio. So I'm looking at the mole ratio between my A and my B. Sometimes it helps if you highlight this or underline it. So I'm looking for B, so B is going to be on the top in this case. So I have 5 moles of O2 over 2 moles of C2H2. Now notice in the second step, I didn't write any labels for this. I didn't label it as C2H2. You're only required to write the labels in an instance where A, you're starting the problem, B, you are changing what the label is. So in this one, I'm going from C2H2 to O2, so I do need to write it, or when you're writing your final answer. So you don't need to write it in every single step, just where the units are actually changing. And then my last step we said was going to be that 22.4 liters per mole again. In this case, I'm going to have liters on top because I want moles to cancel out. So 22.4 liters per 1 mole. And now I'm going to go through and cancel out my units just to make sure I did do everything correctly. So I have liters canceling with liters, moles canceling with moles, C2H2 cancels with C2H2, moles with moles, and I'm left in liters of O2. You plug this into your calculator, the whole top multiplied across divided by the whole bottom multiplied across, putting each in its own set of parentheses. So it'd be parentheses 2.62 times 1 times 5 times 22.4. Close those parentheses, divided by, open a new set of parentheses, 22.4 times 2 times 1. Close that set of parentheses and hit enter. And the answer that you end up with is 6.60 liters. So that's my final answer that does contain correct significant digits. I started with 3, so I'm ending with 3. You do not use your mole ratio for significant digits. You don't use that 22.4. Only your measured values, your calculated values actually go into this. And in this instance, only the starting information has anything that we would use for significant digits. So it's going to have 3 significant digits. One other thing that I wanted to point out here, which is why I highlighted myself a note, is that when you're doing your actual calculations, it's not just the units that can cancel out. You can actually cancel out like numbers as well. So here on the bottom, I have a 22.4, and on the top, I have a 22.4. So rather than put that in my calculator, I could just cancel both of those out. My calculation becomes a lot easier. It's 2.62 times 5 divided by 2. So if they're both at STP, look for that so you can cancel them both out on the left and right, and that makes your calculations a lot easier. Now let's do a couple problems not at STP. These are the more difficult ones. If a problem is not at STP, so then the thing that we need to do here is we need to use the ideal gas law because we can't assume the conditions that it's under. So we'll use the ideal gas law to solve for either the moles or the volume of the gas, depending on what end of the stoichiometry problem we're on. The conditions the gas is under will be given to you if it's not at STP. So it will tell you the gas is stored under this much pressure, this much temperature. The ideal gas law, remember, requires your units to be atmospheres for pressure, Kelvin for temperature, moles for the amount, and liters for the volume. And your constant R is always that 0.0821 liter atmospheres per mole Kelvin. So in our equations, PV equals nRT. So that's what we're going to be using to solve, which means you won't be doing a straight dimensional analysis problem. You'll actually have to start or stop the problem to use this equation to solve for different pieces. So here we have our first problem that is not at STP. It says calculate the volume of the product carbon dioxide in liters. So that's my B. So I'm going to go ahead and identify that as my B. And it said volume in liters. That is produced by the combustion of 14.9 liters of C4H10. So this is my known information. And I have a volume of 14.9 liters. It says the reactants are held at 721 millimeters of mercury and 292 Kelvin. So reactants are the things on the left side of the problem. So I'm going to go ahead and write those conditions right underneath the volume that I've just written out. So my reactants conditions are 721 millimeters of mercury and a temperature of 292 Kelvin. Now we just said that when we're doing these problems that we can't be working in anything but atmospheres and Kelvin. Kelvin is already there, so we need to convert this millimeters of mercury to atmospheres using our pressure conversion of 1 atmosphere over 760 millimeters of mercury. And when you plug that into your calculator, you get 0.949 atmospheres. So that's my pressure in atmospheres. It tells us that the products are collected at STP, so I'm going to make a note of STP over on this side for myself. So now what I'm going to do is I'm going to try to solve this problem. I'm going to look and see where I'm starting and where I'm ending on my mole map. So my A is not at STP and it is a volume. So I'm going to be over here at a volume that is not at STP. That means my conversion factor to get me to moles is going to be N equals PV over RT. Once I'm in moles of A, I'm going to go to my mole ratio for my next conversion factor to get to moles of B. And then my last one said it is at STP. So to get from moles of B to my volume, I'm going to use that 22.4 liters per mole, and that would be my volume. So that's the pathway I'm going to take, and if you look, the first thing that we have to do is not start our dimensional analysis chain, but we have to solve for moles using N equals PV over RT. So I'm going to go ahead and start by doing that. I have all of my information identified up top, so N is equal to PV over RT. My pressure is right up here, my volume right here, temperature here, and we know that R value is always 0.0821 liter atmospheres per mole Kelvin. So I'm going to start by solving this equation and writing it all in now. All right, so there's our equation written out, and if I plug this into my calculator and solve, I get 0.590, and that's moles, and we're still in RA. We have not converted to B yet, so this is still my C4H10. So this is my moles of A now. I went from my volume of A to my moles of A using N equals PV over RT. Significant digits between all of those values that I have there, 3 is the least significant digit, so I have 3 in my answer. So now I'm going to go back to my mole map. I'm now in moles of A. I'm looking to get from moles of A to moles of B, and I'm going to be using that mole ratio step. So I'm going to use my mole ratio from the balanced equation now. My mole ratio, I have 2 moles of A for 8 moles of B. So I'm going to go ahead and plug my equation in by starting with the 0.590 moles. And my mole ratio, we just said that I have 2 moles of my C4H10, and I am converting from one label to another, so I do need to write that label in. And I'm going to moles of my B, and my B is 8 moles of CO2. So now I'm in moles of B. I'm going to go from moles of B to volume, and it is at STP, so I'm using 1 mole is 22.4 liters as my final conversion factor. Over here, moles are on top, so I need moles to be on bottom to cancel. So 1 mole is 22.4 liters. And then I can go ahead and solve from there. So I have 0.590 moles times 8 times 22.4 in parentheses, divide that by 2. When you plug all of that into your calculator, you end up with 52.864 liters, which when you round with significant digits comes to 52.9 liters of CO2. Double check by canceling out your units that this is what you were supposed to get. I have moles canceling with moles, C4H10 with C4H10, moles with moles, and I have liters of CO2 left over. So this is my final answer, 52.9 liters of CO2. So that's your first problem with not STP. And that's what happens when you have your A not at STP. You have to solve by using N equals PV over RT first. This next problem that we're going to do is going to deal with a B value not being at STP. So when the N part of our dimensional analysis is not at STP. So this one tells us we have 708 liters of NO2 held at STP. So this is my A. I know this information. And I have 708 liters held at STP. And it tells me this reacts with water and what volume of NO will be produced if collected at a pressure of 2.42 atmospheres and a temperature of 282 Kelvin. So it's giving me all the information I need to know about my B value here. So B is my NO gas, and I have 2.42 atmospheres of pressure and a temperature of 282 Kelvin. So I'm going to write all of that down. All right, so there's all my information about my B. So now I'm going to identify where I'm starting and ending on my mole map. So going down to my mole map here, I'm starting at an A, which is at STP. So it's a volume at STP, which means I'm starting here on my mole map. And my first conversion factor is going to be 1 mole is equal to 22.4 liters. And that will get me 2 moles of A. Then I need to go to moles of B. That's always my next step, using my mole ratio. And I'm ending with a volume that's not at STP. So I'm ending down here. So to do that, I'm going to have to solve this equation, V equals nRT over P. So I'm going to end my dimensional analysis at moles of B. When I find that moles of B value, I'm going to plug those moles into this equation, V equals nRT over P. So let's start by doing the dimensional analysis component of this problem. I'm going to start with my 708 liters of NO2. So starting with my A value. My first conversion factor said that I'm using that 1 mole is 22.4 liters. So over here, liters is on top, which means in the next step it needs to be on bottom. So 22.4 liters in 1 mole. My next step is my mole ratio step. So I'm going to come up here and see what my mole ratio is. I have 3 moles of A for every 1 mole of B. Nothing's written there, which means it is a 1. So my B is going to be on top. I have 1 mole of my NO, and I have 3 moles of my NO2. Now at this point, we're going to stop the dimensional analysis problem because I need to solve for N here, which is moles of B. This is my N value, and I'm going to use that N and plug it into this equation. So I'm going to go ahead and solve the problem at this point to figure out how many moles of NO I have. So when you plug this into your calculator, you have 708 times 1 divided by, parentheses, 22.4 times 3, close those parentheses. You end up with 10.5 moles with significant digits. That's moles of NO. And again, do your unit cancellation. Make sure that everything's canceling correctly so you know you're doing it right. Liters with liters, moles with moles, NO2 with NO2, and I'm left with moles of NO. So now I'm going to use that equation that it tells me to use, which is my V equals nRT over P. And I'm going to plug in all of the values here so that I can solve. So go ahead and plug in the values. You've already identified them all up here. So I have my T, I have my P, I always have my R. I'm solving for my V. All right, so that's everything plugged in there. I have 10.5 moles times my R value times 282 Kelvin. Divide that by 2.42 atmospheres. I'm going to double check my unit cancellation here. My moles cancels with moles, atmospheres with atmospheres, Kelvin with Kelvin. I will be left in liters, which is the unit that I'm looking for. So when I solve, my volume ends up being 100.5 liters, which when you round with significant digits comes out to 101 liters. And this is liters of NO. So this is my final answer here. Now we're going to try one that mixes up what we've been doing when we were back in school with what we're just learning now. So we're going to do a volume mass calculation, which means I'm combining the mass and volume calculations from our dimensional analysis mole map. So here, our problem tells us we have sodium azide that's used in automobile airbags. The impact of a collision triggers the decomposition reaction that we see above. We're going to calculate the volume of N2. So N2 is my B. I'm looking for information on this, and the information I'm looking for is my volume. And it tells me the volume doesn't give me a unit, so I'm going to go ahead and leave the unit as is. And it's generated at 80 degrees Celsius and a pressure of 823 millimeters of mercury. So I'm going to write down those pieces of information here. All right, so now that I have that written down, I need to make sure that everything's in the correct units. We're using the ideal gas law here, which means that my temperature has to be in Kelvin. So I'm going to go ahead and add that 273 onto that. Plug that into your calculator, and you end up with 353 Kelvin. And then I need to convert my millimeters of mercury into atmospheres using the conversion factor 1 atmosphere over 760 millimeters of mercury. And when I plug that into my calculator, I get 1.08 atmospheres, maintaining significant figures. So now I have all of my information that I need about my B value. And it tells me my A value here is the decomposition of 60 grams of my sodium azide. So I'm starting with 60 grams of my sodium azide here. Whenever you write down a grams value in these problems, the first thing you want to do is find the molar mass of that value, because our step here, when we're going from grams to moles, is always going to involve our molar mass. I know that you guys all know how to do molar mass, so I'm not going to make you do the problem out with me right here, but here's the work if you want to see it. We have 65.02 grams per mole for my sodium azide. So I'm going to write that as part of my information up here. 65.02 grams per mole. So now I have all the information I need to start this problem, so I'm going to go ahead and identify my pathway here. So I'm starting at grams of A, and we just said our first conversion factor is that molar mass of A to get to moles of A. Then I'm trying to look to get to my volume that is not at STP of my B. So following the pathway here, I'm going to need to use the mole ratio to get from moles of A to moles of B. And then I'm going to need to use that V equals nRT over P to get from moles of B to my volume of not STP gas. So that's the pathway I'm going to use. We're going to go ahead and plug in our values now, starting with that molar mass. So I have my value of 60 grams that I'm starting with, of my Na, N3, times its molar mass. And grams is on top in the first step, so I'm going to have grams on bottom, moles on top. So I had 65.02 grams in 1 mole. And my next step is always that mole ratio. So let's go back and look at our balanced equation here. I have 2 moles for every 3 moles of B. So I'm going to put my moles of B on top. So I have 3 moles of N2 for every 2 moles of NaN3. At this point, I do need to solve the equation to find that mole value, because I need moles, which is my N value, to be able to plug it into that equation, V equals nRT over P. So I can go ahead and plug in and solve here. Do your unit conversions, make sure everything cancels out, grams with grams, NaN3 with NaN3, moles with moles. I am solving for moles of my B, which is N2. And when I plug in and solve, I end up with 1.38 moles of my N2. So now I can use this and plug it into my V equals nRT over P equation to find that final volume of my B. I have all the information I need. I'm looking for V. I have my N right here. I have my P right here, and I have my T right here. So I'm going to go ahead and plug all of those in now. All right, so I have it all plugged in. I'm going to do my unit cancellation, moles with moles, atmospheres with atmospheres, Kelvin with Kelvin. I'm left in liters. That tells me I did everything correctly here. So I go ahead and I plug it into my calculator, and using my significant digits, I round my answer to 37.0 liters. And this is N2, which is my B. So there is my answer. 37.0 liters of N2 can be produced by the decomposition of 60 grams of sodium azide under the specified conditions. Now we're going to do a couple of limiting and excess problems. Limiting and excess problems are the exact same as stoichiometry problems in general, except you have to solve the problem multiple times over to actually figure out the final answer. So what you're going to do in a limiting and excess problem, just like we did with limiting and excess problems in regular stoichiometry, just involving our mass and our particle conversions, is you're going to solve both of the reactants for the same product first. So what we're saying with a limiting and excess problem is that if I'm starting with this amount of the first reactant and this amount of the second reactant, which one's going to run out first? So to figure that out, you need to figure out how much each of those reactants can produce of the same product. The one that produces less product is the one that's going to run out first, and then that's going to be our limiting reactant because it limits the amount of the product that we have chosen that we can actually produce. You don't need to solve for both products because if it's going to run out first, it's going to produce less of both of those products. So you pick one, and if the problem specifies, great, then you do the one the problem is asking for. If not, just pick one of those products, solve both of the reactants for that same product. Then you're going to identify which one is limiting, which is excess. The limiting is the one that produces the smaller amount of product. I want to be very clear here that it is not the product that is the limiting, it's producing the smaller amount of product. So the one that you started with that produced the smaller product, that is your limiting reactant. Reactants are on the left side of the equation. The other one is going to be considered in excess, meaning I have extra of it, it's not going to run out, and when I'm done, there's going to be some left over. Step 2, if it asks you to, you'll solve for anything else in the problem using the limiting reactant. So once we figure out what the limiting reactant is, that's the one we're going to be starting the rest of our equations with. And step number 3, solve for the excess. So for this, what you're going to do is you'll start with the limiting reactant, solve for how much of the excess reactant you actually will use up. So I'll start with one reactant, solve for how much of the second reactant I need to use up all of my limiting reactant. And then I'm going to subtract that value from how much of the excess I actually had available to me to begin with. So if I started with, say, 50 grams of excess and I solved and I only need 40 grams of it, 50 minus 40 is going to give me 10 grams that will be left over when the reaction is done. This is a complicated process, so we're going to start with an easier problem at STP here. So we have our balanced equation where I have a question asking me what mass of my zinc oxide is produced from 418 grams of zinc sulfide and 185 liters of oxygen stored at STP. So this is nice and easy. We are at STP. And then it wants to know how many moles of the excess will remain when the reaction is complete. I'm going to go ahead and start this problem by writing down all of the information I know, just like I've been doing. And it's asking me for what mass of zinc oxide. So this is going to be my B in both scenarios, and I'm looking for the mass. And I said whenever we have mass, we're going to go ahead and write down that molar mass because I know that we're going to need it somewhere in the problem. So our molar mass for zinc oxide is 81.39 grams per mole. And you can see the work done for this down here, as well as zinc sulfide if you want to go and look that over. So my molar mass written down there, and then I'm going to write down my A values. I'm going to have two A values. I'm going to start with my 418 grams of zinc sulfide in one of them. So this will be A1, and I have 418 grams, which means I need a molar mass. So I'm going to write down my molar mass of 97.46 grams per mole. And then the second piece of information it gave me was that I had 185 liters of oxygen, and it was stored at STP. And this is going to be my A2. So I'm going to do this problem twice. I'm going to go from A1 to B, and then after I've solved that, I'm going to go from A2 to B. And I'm going to compare the answers that I get for B and see which one of these is going to run out first because it's going to produce less of my zinc oxide. So I'm going to go in order here. I just like to go from left to right. So I'm going to start with my 418 grams of my zinc sulfide. So looking at this, I'm going from my A1, which is a mass, to my B, which is also a mass. So the path that I'm going to take for this one, I'm starting with grams, and I'm going to go to grams of B. So I'm going to follow using my molar mass to get to moles of A, my mole ratio to get to moles of B, and my molar mass of B to get to grams of B. So this doesn't involve volume at all. This one's just very simple molar mass conversions. So we're going to start by writing down our molar mass, or our mass. We're going to start by writing down the mass that it gave us, 418 grams. This is grams of ZnS, which is our zinc sulfide. My first step was molar mass. Grams is on top here, so grams is going to be on bottom here. My mass was 97.46 grams per mole. Then I'm going to use that mole ratio step. So my mole ratio here, I have 2 to 2. So I have 2 moles of zinc sulfide for 2 moles of zinc oxide. Zinc sulfide is going to be on the bottom to cancel out. And 2 moles of zinc oxide on top. My moles of B is always on top. My last step is that molar mass for my B, and I have moles on top here, so moles has to be on bottom. So I have 1 mole having 81.39 grams in that final step. I'm going to run through and cancel out my units, just make sure I did everything correctly. So I have grams canceling grams, moles canceling moles, zinc sulfide, moles with moles. I'm left in grams of zinc oxide. So I did do my work correctly. I'm going to go ahead with significant digits, plug this into your calculator, and you end up with 349 grams of zinc oxide. So now that part of it's done. I can leave that alone for now, and I'm going to go ahead and start with my A2. So I'm going to solve A2, and I'll use a different color for this one. Let's go to blue. So I'm going to go from my A2 to my B. So in this scenario, let's go back to our mole map. I'm starting with a gas at STP, and I'm ending at a mass. So I'm starting here at a gas volume at STP. My first conversion factor is going to be that 1 mole is 22.4 liters, and I'm looking to get to grams of B over here. So the conversions I need, 1 mole is 22.4 liters, gets me to moles. Then I'm going to need that mole ratio again to get me to moles of B, and then I'm going to use molar mass of B to get me to grams of B. So I'm following the blue path this time. So let's go back to our problem here. We're going to start by writing down our information. So I have 185 liters of my O2. First conversion factor is going to be 22.4 liters is equal to 1 mole. Liters has to be on bottom to cancel out. Next step is going to be that mole ratio. So I have my 3:2 ratio here. B is always on top, so 2 moles of my zinc oxide for every 3 moles of my O2. And then my last step is going to be the same as it was above because I'm ending with the same part of the problem. So I need that molar mass, which is 81.39 grams per 1 mole. So when you're doing these problems, you'll notice that the ending, if I'm solving for the same product, is always going to be the same. So this part of the equation is the same as this part of the equation, which means you can just copy it on down and it makes your life a little bit easier. So when I plug this into my calculator and solve, and I use my correct significant digits, I get 448 grams of zinc oxide. So now this is the part where I stop and compare. I'm looking at my 2 answers, and I want to see which one of these answers is the smaller answer. The smaller answer is going to be the one that's the less amount of product produced, which means the thing that I started with is going to be my limiting reactant. So 349 very clearly smaller than 448, which means that my limiting reactant is my 418 grams of zinc sulfide. I'm going to run out of this 418 grams of zinc sulfide before I run out of oxygen. Notice that the numbers, even though I started with 418 of one and 185 of the other, that's not important. You can't tell just by looking at that value and predict which one you're going to run out of first because we have different amounts of moles of each required. So I have 418 grams of my zinc sulfide. I'm going to label this as my limiting reactant, which you can just write LR for to label it, which means that this one's going to be my excess reactant. This is the one that I'm going to have extra of by the time the reaction is done, and we use XS for the abbreviation for that. So now that I've looked at these and I've analyzed, I figured out which one's my limiting reactant, and I figured out which one's my excess. I'm going to do the second part of this problem, which asks me how many moles of my excess remain when the reaction is complete. To figure that out, I need to figure out how much of the excess is going to be left over and then convert that into moles. So what I need to do, if we go back to our steps up here, to solve for the excess is start with the limiting reactant and solve for how much of the excess reactant we're going to need to use during the reaction. So I'm once again going to be starting this problem with my limiting reactant. So this is going to be an A3. We'll keep it in pink here. So now I have A3, and my B is the excess reactant. So I'm solving from zinc sulfide to oxygen in this case. So I'm going to go ahead and do that on the next slide here because I left myself a little bit of room. So I'm starting with 418 grams of zinc sulfide, and I'm going from grams to liters at STP. So I'm going to go down here. We'll use another color. Let's try yellow. So I'm starting with grams, and I'm going to go from grams to liters at STP. So I'm ending down here. So following my pathway, I'm going to go molar mass to moles of B using my mole ratio. And then I'm going to use 1 mole is 22.4 liters to solve for my volume at STP. So I'm following the little yellow pathway there. So first thing I need to do is use that molar mass of ZNS, which I have up here is 97.46 grams per mole. Grams needs to be on bottom, so 97.46 grams goes on bottom. 1 mole goes on top. Then I'm going to use my balanced equation to figure out what my mole ratio is. So my mole ratio here, I have 2 moles of zinc sulfide for every 3 moles of oxygen. So my B goes on top, which is my oxygen, 3 moles of oxygen for every 2 moles of zinc sulfide. And then my last step was that 22.4 liters per mole. Moles needs to be on bottom to cancel out. 22.4 liters goes on top. I'm going to go ahead and do my unit cancellation here to make sure I did everything correctly. Grams with grams, moles with moles, zinc sulfide with zinc sulfide, moles with moles, and I'm left in liters of O2, which is where I'm looking to be. So I'm going to go ahead and plug this into my calculator and solve now. When I do that, I get 144.11 liters, which with significant digits rounds to 144 liters of O2. Now there's something I want you to write after this every time you solve, and you're solving from your limiting to your excess. This is how much you used. This is not your final answer. So when I'm doing this problem, what I'm saying essentially is if I start with my 418 grams of zinc sulfide, the amount of my oxygen that I will need to use in order to use up that entire 418 grams is 144 liters. Up here, I'm starting with 185 liters available to me, and I'm only using 144 of that is what I'm saying. So if I want to figure out how much is left over, I need to subtract those two values. So I started with 185 liters. My problem telling me that information right here. I've started with 185 liters, but I'm saying I'm only using 144. So 185 liters minus 144 liters. Plug that into your calculator, and you end up with 41 liters of O2. Now this is my excess. This is how much is left over. So when the reaction is done, I'm going to have 41 liters of O2 left over inside of that container. But this isn't what that problem asked us for. We didn't get asked for liters, so we need to convert this to moles. It asks us specifically for how many moles of excess right here, how many moles of excess remain when the reaction is complete. So we need to do one more step, and I need to go from liters to moles, and this is a gas at STP. Remember, our oxygen, it tells us way up here, is at STP, which means I can use that conversion factor 22.4 liters per mole. So liters is on top here. Liters needs to be on bottom of the next step, 22.4 liters, 1 mole. And when I plug that into my calculator, it tells me that I have 1.8 moles of O2 in excess. This is my final answer. So as you can see, it's the same process over and over again. It's not entirely difficult calculations, but it is long. Each one of these problems does take a while. And this is an STP problem. I've got one more problem for you guys before I free you here. And this is one that's not at STP. So again, it's the same basic steps. We're using the exact same balanced equation. So I already copied down our information that we needed here about our molar mass because it's the exact same thing. But now this problem is going to ask us if it's not at STP. So we're going to do this a little bit differently. So our equation says what volume of our sulfur dioxide would be produced from 311 grams of zinc sulfide. So I'm going to write that in, 311 grams, and 125 liters of oxygen. So that's stored at STP. That's good. That's less work for us. We'll write down STP. If the SO2 is collected under 1.55 atmospheres of pressure and the temperature of 32 degrees Celsius. So now I'm looking for SO2. I'm looking for a volume over here. And it gives me my pressure and my temperature information, so I'm going to go ahead and write that in. So now with this information, I need these to be in the correct units. Temperature always has to be Kelvin, so I'm going to go ahead and add that 273 onto it, and I end up with 305 Kelvin. And then this is already in atmosphere, so that's correct. We don't need to do any conversions there. So I have everything written down now, and I'm going again from an A1 and an A2 over to the same B over here. So this is going to be my B in both problems. So I'm going to do this problem twice, once starting from A1 and going to B, once starting from A2 and going to B. And like I said, I like to go in order, so I'm going to go ahead and start with that 311 grams. So looking at our chart, I'm going from a mass with A1 over to a volume that is not at STP for my B. So I'm going to start with my mass, which is over here. and I'm looking to get to a volume that is not at STP over here. One of the things I'm going to do in this problem to make my work a little bit easier so I don't have to solve this V equals nRT equation twice is I'm going to solve for moles of B, and I'm going to end there and compare those values, because if my moles of B is less, that means my volume of B will also be less, and then I don't have to use this equation twice. So I'm actually going to solve from grams of A to moles of B first. So grams of A to moles of A, and then to moles of B, I need my molar mass and my mole ratio step. And then I'm going to stop at moles of B for now, figure out which one is less, and then just solve that one for my volume of B, just to save myself some time. So I'm going to start with my 311 grams here of my zinc sulfide. Use my molar mass as my first conversion, so moles have to be on top because grams have to cancel out on the bottom. 97.46 grams. Use my mole ratio. So my mole ratio here, I have 2 moles of ZNS for 2 moles of SO2. So my SO2 goes on top, ZNS on bottom. And then I need to stop at this point, because if I'm solving the next part of the equation, I would need my N value, my mole value here. This is solving for N so that I can put it into this part of the equation, V equals nRT over P. So I have to solve for my N at this point. So I do my 311 times 1 times 2 divided by 97.4 times 2. You can actually cancel out both of these 2's. So if we do some unit cancellation here, I have grams canceling grams. I have moles canceling moles, ZNS with ZNS, and I actually have 2 canceling with 2 here. So then I'm left with moles of SO2. So when I solve this, I end up with 3.19 moles of SO2. So now I'm not going to solve for the volume just yet, because I want to figure out which one has less moles, and then that's the one I'll use to solve for the volume to save myself some work. So I'm going to go ahead and start with my A2 at this point. My A2 tells me I have 125 liters at STP. So I'm starting with a gas that's at STP, and I'm looking to get to a gas that's not at STP. So we'll use red here. So I have a volume at STP, and I'm looking to get to a volume not at STP. So I'm going to start using 1 mole is 22.4 liters. That gets me to moles. I use the mole ratio to get me to moles of B, and then I would use that V equals nRT to get me down to volume of not STP if this one produces less. We'll see which one does. So I'm going to start by writing down the starting information that it gave me. We'll pick a different color here. So I have 125 liters of O2 times that 1 mole is 22.4 liters conversion factor, liters on bottom so that it cancels, times that mole ratio. So coming up here to my mole ratio, I have 3 moles of O2 for every 2 moles of my sulfur dioxide. So on top, 2 moles of sulfur dioxide, and on bottom, 3 moles of oxygen. So now I'm going to do my unit cancellation here. Liters cancels with liters, moles cancels with moles, O2 with O2, and I'm left in moles of SO2, which is what I want to be in so that I can compare these two values. I plug in and I solve, and I end up with 3.72 moles of SO2. So now looking at these problems, seeing what do they really mean, if I start with 311 grams of zinc sulfide and I assume that I have excess of everything else, I could produce 3.19 moles of SO2. But if I start with 125 liters of oxygen and assume I have excess of everything else, I could produce 3.72 moles of SO2, which means the one I'm going to run out of first is going to be the lesser value, 3.19 moles of SO2. So the limiting reactant has to be my zinc sulfide over here. So my limiting reactant, is my zinc sulfide. That's the one I'm going to run out of, which means that my excess reactant is my oxygen. All right, so now that we figured out which one's the limiting reactant, that's the one that we're going to solve and figure out the volume for. So I'm going to use that equation down at our chart here. Volume equals nRT over P. It's right here. So now, rather than solving this problem twice, I've saved myself some work. I don't have to solve it again. I can just use this N to figure out what the volume is. So this is the limiting reactant. So V equals nRT over P. I now have my N. All of my other information is up here. So I have my temperature and I have my pressure right here. And I always have my R value. So I'm going to go ahead and plug those into my equation here, and then we can solve. All right, so everything's plugged in there. So I'm going to go ahead and do my unit cancellation now. Make sure I solve this right. I have moles with moles, atmospheres with atmospheres, Kelvin with Kelvin. Leaves me just liters on top there, which means I did put everything in correctly. So I go ahead and I plug this into my calculator, making sure I'm using my parentheses correctly. And I end up with 51.5 liters of sulfur dioxide that I've produced. So now I've answered the first part of the question. I figured out what the limiting reactant was. I used that limiting reactant to solve for my volume, and the amount of volume of sulfur dioxide that I'm able to produce at 1.55 atmospheres of pressure and a temperature of 32 is going to be 51.5 liters. So I answered the first part. Now we need to answer the second part of the equation. How many moles of excess reactant remain when the reaction is complete? So to do this, again, we're always going to start from our limiting reactant and solve for our excess reactant. We said our limiting reactant is that zinc sulfide. So I'm going to have an A3 here. We'll pick another color. So I'm starting from this A, and I'm going to the excess, which is the other reaction, or reactant. So I'm going to go from zinc sulfide to my oxygen. So I'm going to go ahead and set that up down here. I'm starting with a mass, and I'm ending with a volume that is at STP, which is nice and easy. So starting with my mass, and then ending at a volume at STP, right down here. First conversion factor is going to be that molar mass. That gets me to moles of A. Then I need my mole ratio to get me to moles of B. And then I need that 1 mole is 22.4 liters to get me to my volume. So no funny business here. This is a nice and easy one. So I'm going to do that on the next slide here, starting with my 311 grams of my zinc sulfide times my molar mass. Mass has to be on bottom, so I have 1 mole over 97.46 grams. And then I need that balanced equation to find my mole ratio. So I have 2 moles of zinc sulfide for every 3 moles of oxygen. 3 moles of oxygen on top for every 2 moles of zinc sulfide on bottom. And then my last step we said is going to be that 22.4 liters per mole. Mole has to be on bottom to cancel out. So I'm going to go ahead and double check my unit cancellation here, make sure everything cancels out. Grams with grams, zinc sulfide, moles, moles, moles and moles. I'm left in liters of O2, which is what I'm looking for. So I'm solving for my liters of O2, and I end up with 107 liters of oxygen. And remember, I said we always want to write used underneath this to remember that this is not our final answer. This is just so that we can compare to the amount that we started with so that we know how much of a difference there is between those two. So I'm using 107 liters if I'm starting with 311 grams of zinc sulfide. But available to me in the problem, it tells me I had available 125 liters of O2 available. So if I started with 125 liters and I used 107 of those, I subtract to find the difference between them, and I end up with 18 liters of O2 that's actually my excess. So when you're doing this, you always want to do available minus used equals the excess amount. So I'll have 18 liters of oxygen left over when all is said and done. But again, it didn't ask me for my final answer in liters, so I need to do one more conversion. It asked me how many moles of it I have left over. So my final conversion, this is at STP, so times 1 mole over 22.4 liters will give me my final answer. So I plug that into my calculator and I end up with 0.80 moles of oxygen that is not being used. So this is my final answer. This is my excess amount of oxygen after this reaction is complete. All right, now you guys have a worksheet on Schoology to practice with this, so go ahead, give that a try. Reach out if you have any questions.